इसमें अच्छा है।
हेलो विजिबल है। हेलो विजिबल है।
विजिबल है देखिए
कोड
बोर्ड व्हाइट बोर्ड विजिबल है। व्हाइट बोर्ड ये वो शेयर करना है
हो गए।
फॉर्मेट है ना, ठीक है स्टार्ट कर।
पीपीटी नहीं दिख रहा है इसमें सर चेंज करेंगे ना। हां बाद में एंटर नहीं कर नीचे रहेगा।
सर आप ये इधर से आप ज्वाइन करके चेक कर लीजिए।
ये एक्चुअली
इंटरनेट नहीं चल रहा है आपके स्क्रीन
ठीक है। आज इसकी इतनी जरूरत नहीं है।
ओके
ये आप लोग बाद में भी देख सकते हो, मोस्टली तो बोर्ड ही है जो है।
ओके ठीक
इट्स जस्ट फॉर रेफरेंस है तो मेरे और आपके लिए।
तो आज कुछ स्टूडेंट्स अभी हैला में ऑफिस में एक्चुअली होता आज कुछ
वो नहीं आ जाता।
टूल नहीं आता है।
ठीक स्टूडेंट एक्चुअली
ठीक है, अपन करते हैं स्टार्ट।
गवर्नमेंट जी का क्या है आपको कोई देता है रिव्यू नहीं रिव्यू है
ओके, मेरे आने से दिक्कत तो नहीं है किसी को?
नहीं
ठीक है, अपन स्टार्ट करते हैं। ठीक है ओके, तो अभी तक व्हाट वी हैव स्टडीड, we studied linear regression, and then we had a loop of logical regression then, and we already know that this was for regression problem was for basically predicting cell bees, for example, or anything which is in continuous forms, right? And logical regression was basically for classification. Now we're gonna see a totally different kind of algorithm, which is basically known as decision trees and ensemble methods. And how many of you have known already some or heard of this term, decision trees? This is an random forest, right? So there is a small caveat. So before going on to understanding what is decision trees, try to understand what exactly the tree is. This is what this we have seen in our pre-tech. In general, a tree is something whose shape looks like this. I mean, in general, this is the tree. I mean, this is level starting, level 0, and then we would have level 1, and so on, right? So the whole decision tree algorithm is basically kind of creating trees. So overall, your algorithm will work in form of solving the problem in form of trees. So let's see how it is. So before that, some basic terminologies we want to see how a tree is denotes. The very first node, which always starts from label 0, this we call as node. Also, as we the very first word root. These are roots, right? You also want to see. So this is your root node, and then these will be further divided into subparts. The nodes which lie between starting and between end, these categories basically these are the intermediate nodes, and the last one which ends the tree, these are the terminal nodes. Or this has nothing to relate with the machine learning. This is in general a tree is called this, right? Intermediate nodes, also decision nodes. Right. Okay. Now try to just see some some problem before going into decision trees. Uh, let me see my list. Okay, let's start over. So let's try to understand something. So there is a flower which is known as iris. Iris is a kind of flower. It has three categories. First is setosa, another is the virginica, and third one is the versicolor. So, for example, if you as a human eye gonna see setosa, virginica, versicolor, you won't be able to differentiate. Right? There's a very minute difference between the petal length and the sepal length. So I mean, this is the this is the leaf of that. It would be, and then there would be petals. So a normal flower has sepal and petal, right? And there's a very minute differences between setosa, virginica, versicolor, right? So suppose as a human, if we asked, okay, can we make some kind of solution so that you are able to differentiate a flower, the iris flower, into the categories, right? And you have been given what? You have been given, petal and sepal. So iris data set. And would have working, it's been really faster. Okay, ठीक है. So in general, a leaf is something like that, and there are parts. Yeah, you will see some parts, right? Like, so what we have four things here. I mean, this is the height, and this is the width, right? And then this future, we have height, and we have width, right? So in general, the iris data set is provided to in the form of sepal length, or I can say height, sepal width, petal length, and petal width. And we have provided some numbers, for example, 0.25, 0.26, 1.25, 1.75. And this way they are provided you say n rows. Now we have been asked that based on such number, can you create some kind of solution that you can say, okay, this category is setosa, this is virginica, or this is versicolor. Then what we see, we looked at the data. And what we found that, okay, by looking at the data, if petal width, and this as some researcher working on iris data, he saw that if petal width is less than 1.45, 1.45 mm or cm, if petal width is less than 1.44 mm, then all the flowers are the categories of setosa. So this we see in the data, right? After we getting research. And then all the cases which this is yes condition, all the cases which doesn't follow this condition, they could be virginica and versicolor. Then this researcher found that, okay, I mean, this part is sorted. I'll look at the data. I'll check, okay, whoever the petal width is less than 1.45, they are setosa for sure, right? If that is this condition is false, then that flower could be virginica or versicolor. Then what he found in the data, okay, if petal length is less than 1.75 mm, so to say, then this is versicolor and this is virginica. Right? This way, based on what? Based on just two conditions, we segregated the whole data sets into three categories, right? So if I get a new row, I'll check, okay, petal width is 1.45. Okay, it's less than that. It is setosa for sure. We end the decision. It is setosa. But this condition is false. Now we will check the second condition. This is what if the petal length is less than 1.75, then this is versicolor. If this condition is false, this is virginica. Now this is how you if you now try to relate this thing with a decision tree, this becomes your root node. This is your root node. Was the very first node which you start taking under the consideration. And then this is a node where all the Satosas plants were classified. So every decision ends here. Therefore, this node becomes a terminal node because after that there is no decision, right? This is the end. But here in this category, this is the decision node and this is a terminal node. Now, this is a very small example. We, as a human, we just looked at the data. The researcher did, they plot the graph. They plot the graph here, say petal length, petal width, and they plotted all the points. This is all the plot points. This is petal length and width. Now they say if this is less than 1.45, the very first condition, this instance becomes your Petosa. Then petal length 1.75. We mark over here. Less than that becomes virginica, versicolor, whatever, and this becomes virginica. So in general, with the help of decision trees, you created the decision boundaries, right? This part is exactly right. So this is how a general decision trees work. Now, point is that this okay. I'm you everybody can have look at all the rows, all the four data, they can plot it. But what if your data is 100 columns? Now you cannot decide okay after which column should I take the root node.
Yes.
I mean there could be n number of nodes which can give you different results. I mean if you would have started with say simple width, the whole decision trees would have gone into a different direction. You consider sepal width, then you may consider sepal length or sepal width, petal length. There are different combinations. So this part were taken care by the decision trees, where they automatically decides which node should I start. Then after that, which node should I take? Here we started with petal width, and then we took petal length because this was clearly visible in a small data set. If there are 100 columns, you have to decide, shall I start with column 1 as a root node or shall I start with column number 45? After column number 45, shall I go with column number 10 as a second boundary? And 100 columns, you cannot plot it or see. But there has to be some algorithm. This was a decision tree came into the picture. So automatically having some algorithm, which you basically execute, and they will create all the tree and give you the best tree. That start with column number 45, then go with column number 10. End goal is what? End goal is that we want our terminal nodes to be segregated properly, right? For example, if you are solving a problem in which you need to decide, in our case, the problem was to decide into three flowers: Cytosa, Virginica, and Versicolor. There are three classes. So end goal was that your terminal nodes has to be that one denotes Cytosa, one Versicolor, and Virginica, right? So this is basically a classification problem. Eventually, you are doing a classification, right? If in your case you would be solving a problem, for example, spam or not spam, the final terminal nodes would be just two: spam or not spam. The same thing which we already discussed. We could have started if we had or a lone defaulter. Our very first node could be is any default in the past, true or false, right?
Yes.
If yes, that default in the past. Second node might be how many times. Eventually, end goal is that find the best decision tree so that you would be able to classify your final predictions into the proper groups of defaulters and non-defaulters. This is the end goal of any decision tree, to classify into different categories. Logic regression helps us do that. in logic regression also we did it into two classes. Right? I mean defaulter, non-defaulter. But there we were basically created a whole solution. We use the thetas, we use the parameters. But in this case, you won't be seeing any theta. So sometimes we also call it non-parametric. I mean, we are not involving thetas. We are not, updating weights here. It is pure decision tree which you need to come up. How we come up, we will see. Now, this is what decision tree.
So, Rajkumar,
Yeah.
so the logistics regression technique, will it go combination with the decision tree? Or
So this
both of them are classification problems.
Yeah. So when you want to solve any problem, you would be having the option that you could start with decision trees, or you could start with logistic regression. They are different algorithms. Then you will see, okay, in my case, logistic regression is working well as compared to decision trees, or decision trees is working well. So this is different algorithm, and goal is same classification. However, we will see decision trees also helps us do the regression. So decision trees do.
When we generally talk about AI and ML, we see some machine learning that layer by layer, some the diagram where one node is connected to multiple nodes and kind of deep layers. So is it same as this one, or that thing is totally different?
That is different. The layers which you have seen, that's they are something.
Yeah.
They are
Yes.
splitting into two. So that's the part of neural networks, artificial neural networks, and precisely they come under the categories of deep learning, which is a subset of machine learning.
Okay.
Right. So
But my question was, like, for example, if we have uh, the flower, the example what you said, if there are like 10 different categories of flowers, means here it is 3, but if there are 10 different, so at the end your terminal node should be, let's say 10.
should be
At the
10,
end.
right?
But can I first use, if I have to choose an algorithm, maybe to reduce the complexity, first I would choose a sigmoid function or a logistic regression. I would do a broader classification, like maybe 5 and 5. Or maybe I'll take 15, for example. If there are 15 different, first I'll do 5, 5, 5. Then it will be like another set. So then can I combine the decision tree system somewhere in between? Or if I start with the logistic regression, then I expect that logistic regression itself will do 15 classification. Or if I take a decision tree, then decision tree will do 15.
So you can combine these two algorithms separately, not in between. Logistic regression doing its work, decision tree is doing its work. First goal is to make the whole algorithm, whole system solution simple. So we do not think of intermediating both the things. However, as a practical approach, logistic regression is the very first we always try, because that most of the cases that will help you. And later we will see that in which case you should go with logistic regression or decision tree on a theoretical understanding.
Yes.
Rest is just practical. Okay. But decision trees you will see comes with a lot of problems. However, this becomes a basis of the next very heavy algorithms like random forest, etc., gradient boost. So decision trees are the base, and these algorithms which I see, these are called as ensemble methods, ensembling multiple things. So you multiple many decision trees to get the best, right? So basically you create one decision trees. It says that this guy is a defaulter. You create one more decision trees that with some other root node. That guy says, okay, this guy is not a defaulter. You create 100 decision trees. Then you will see out of 100, 80s are saying that this guy is okay. Then you will go with, you make your confidence stronger by making 100 decision trees. Each decision tree trying to capture different aspect, right? And later, and this is called as merging different decision trees into one, and that are called as ensemble methods. That's why I mentioned decision trees and random forest. Random forest is the next successor of decision trees, in which you use hundreds, thousands of decision trees, right? That we're gonna see. But understanding decision trees is very important.
So, one more question. So in logistics regression, we talk about the confusion matrix. So they value.
Yeah.
So there will be the accuracy or the recall. So even in this case, there should be something like that, right? So
Same matrix. Any matrix, confusion matrix is irrespective of the eventually you're gonna have 0, 1, 0, 1. You're gonna have false positive, false negative. So that matrix remains everywhere. At whatever algorithms, right? And even in what Gen AI, chat GPTs, you make some wrong prediction, right? So that's also kind of 0, 1 category. Okay, so one example, I don't know if online colleagues will be able to see, but I'll make based on weather outlook, humidity, wind, should we play tennis? Right? A simple, just because now right now we are just trying to understand the trees. So there could be three outlooks: sunny, overcast, rainy. Right? If it is sunny, then there could be humidity. Then if humidity is high, we are not gonna play. If it is yes, if it is low, we're gonna play. Now overcast, you won't be able to play tennis. And if it is windy, then if it is strong, no. You know, there are different categories, right? So this is small example. One more example. Project management decision helper. Should I start this project? Yes. If it is important for the company, yes. If it is too risky, yes. Consider not to be involved. So these all are the decisions you are taking at each level, right? Again, this is a normal example how a decision varies. I mean, nature of decision trees is totally human intuition. How you think, you always think step by step. Shall I do this? Okay, if I do this, will anything be compromised? If yes, okay, no. This is how we take business decisions. Like the whole human intuition would be built on decision trees. Okay, now before coming to now we gonna see some very I mean mathematical or very you know good thing here. We're gonna understand the concept of entropy. Now slowly now I'm trying to delve into the technical aspect of finding the nodes. I mean, shall I go with root one, column five? So before that, I need to understand a term which is known as entropy. You already have heard of entropy, right? Okay, just tell me one thing. If there is a bucket, there is a bucket in which you do not know what is inside. I know that there are 10 coins, five red, five blue. Right? Now another bucket, 10 blue. You know this part that okay, five red, five blue is there, 10 blues are here. You have been asked to pick one, in which cases you would be more confident that I am getting blue for sure. This one, right? And this one, 50-50. So here in this case, impurity is nothing but you can call it is as the impurity or the noise. Here the noise is too much. I mean, you are not sure. This class is 50-50 divided. Too much noise in it. Or I can say too much impurity. What do you mean by impurity and purity? Purity means if your class consists, your bucket consists of pure one class. If I consider a terminal, these are our last terminal nodes, right? If I want to, and this is our blue, green, red. This guy has five blue, two green. This guy has 10 blues, this green, blue, blue, and red. This guy has nine red and one green. Ideal case was that this guy should contain all the greens, this guy should contain all the blues, this should contain all the reds. Only this class, the blue class, this is all 10 blue, zero red, zero green, right? I mean, this is a pure class, purity. I mean, there's nothing else, no green, no red. However, in this class, five green, two blues, there are some impurity. This is impure class. And this guy, nine red, one green. Impure class is still close to purity. The best scenario is this one. This is the second best. This is third best. So this is known as purity and impurity. Entropy is the factor which measures how pure your class is. Right. This is a goal. Now, why it is necessary to understand the entropy here? Suppose initially I am building a solution where I need to divide solution into red, green, blue. Initially, your very first bucket contains all. Just take two example. It contains 10 red and 10 blue. Right. Now you apply some. You choose some node here, some decision taking node, and finally your bucket comes out to be this bucket, uh, five red or maybe eight red, two blue, and this bucket two red, eight blue. If I calculated some entropy here, just try to understand. This node splits it into two categories. I calculated entropy here, and then I sum up this entropy. This is parent, this is child one, child two. So child entropy equals to entropy of child one plus entropy of child. Just for example, this is entropy of parent. Now, just looking at the entropy, what do you think if I subtract entropy parent minus entropy child, whether it has to be higher or lower? If I can say that these are pure or impure class. So if I am able to make this class pure, entropy would be lesser,
Yes.
right? Entropy parent minus entropy child. Differences is lesser. Overall, entropy parent minus entropy child. If this is lesser, this whole thing would be higher. If entropy child is too much, I mean too much impure classes, it means entropy of child noise in the class is too much. So overall difference is lower. So this part is known as information gain. So information gain. Okay. So what my goal is to have the nodes such that my information gains remains higher. Idea is simple. My child impurities has to be lesser. If your node, the decision taking node, is able to make buckets separate, even you already reduce the noise. You reduce the noise, you can gain more information. So that's the case. So if the simple thing boils down to information gain. Information gain is nothing but entropy of parent minus entropy of child. If there are three childs, it would be entropy of child one plus child two plus child three, right? And higher information gain means better split. And what do you mean by better split? You are able to segregate your classes into pure classes. And in practical scenario, there would never be the case that you are able to solve all the defaulters into one bucket, all the non-defaulters. There would be a false positive, right? False negative. But our overall goal is to, have better splits, right? See, this is the graph.
With the better information gain, it means that the algorithm will predict much accurate. So it means that the randomness or the noises are reduced. When we start to subclassify, so the randomness entropy will
Reduce of the child. It means you are able to segregate it better.
better.
And now this we are doing for whom? This we are doing for the decision node. For example, okay, I mean he decided that let's choose column number 10. I mean we have 20 columns. You decided column number 10. So what column number 10 will do? If column number 10 is less than 50, I mean this is how the boundaries will make. If this is less than 50, class A, else class B. Now you will calculate initially the entropy of column number 45, right? And then you will see how, based on the condition he provided, these many were going to the class A. Then you will calculate the entropy of child one, entropy of child two. You will do the information gain. You calculate information gain for column number 45. You the calculated information gain for column number 30. And we eventually found column 30's information gain is better, is higher. It means column number 30 is a better splitter, right? So column number 30. Now this is how, now this boils down to whom should we start? I mean, if there are 10 columns and just there are 10 columns, who should be your root column? This is the first category. So what we will do, we will calculate information gain for all the columns. And we will choose the root node whose information gain is higher, right? Now, first question, this mathematically is better to tell. Entropy's formula is nothing, it's kind of very intuitive. It's minus E log base to the base of 2 P. P is the probability, right? So for example, if your parent initially I provided you data of 1,000 rows. We will continue with the example of lone defaulter. In my case, 1,000 rows. We have m equals to rows. In my data, I have taken the cases where the class defaulter is 100, class non-defaulters is 900, right? So entropy of parent would be minus probability of defaulter 100 out of 1000 log 100 out of 1000, right? So this is basically 0.1 log 0.1. And then you calculated entropy of non-defaulters, right? And then you sum it. So that becomes the entropy of your parent, right? Now at this point, this we do for all the columns, and I see, okay, some column giving me higher information in, that becomes my very first decision maker. Okay. So suppose the column was is person ever defaulted? Yeah, something. This ever defaulted or how many times? Suppose it boils down to the cases. Yes, no. Now this bucket contains 40 defaulters, 800 non-defaulters. But this could be a very probable candidate of a future. Is this person defaulted more than 3 times? So he's likely a defaulter in the previous 1 or 2 years. So therefore, what I see, out of 900, almost 800 cases came into this bucket, and remaining 60 defaulters here, 60 defaulters, 40 and 100. So you will calculate the entropy of this guy. This entropy again would be same formula, same formula. So entropy of child, or this would be entropy of child 1 plus entropy of child 2. However, this thing would be weighted. 840 cases have landed here, 860. So we weight it 860 upon 1000. Here 140 cases landed, 140 upon 1000, right? This becomes the entropy of child. Parent minus child, you will get the information gain. Right. After this becomes your decision root node. This is root. Try to understand with the very first diagram which we see, root, decision node. Now we will see after this, column 1 is already done. Suppose this was column 1 itself. Now we are left with 9 more columns. Suppose in my data, if we have 10 columns, 10 features. Now we will do the same stuff. This is parent. Now, shall I go with column number 5, right? Then you will try to choose column number 5. You understand? I mean, consider this part is done. Forget this part. This becomes your parent. Every level you will choose the best probable candidate.
Okay.
Right. Eventually, goal is to segregate into the best mutually pure set of classes. This part is clear. So here, maybe after this, column 5 gives you the best information gain. Then your column 5 decision will become the condition. Condition could be if column 5 greater than, if suppose column 5 is salary greater than 50,000, 40 defaulters here, 600 defaulters here, 40, 20. Likewise, you will decide here. So basically, each tree will spread. Now you may ask then, how many times shall we go down? I mean, there could be end. I mean, it's not make sense to be consider 90 futures here. So we will see how to tune. In linear regression logic, we see that there are alpha learning rate. Here also there are some parameters.
Like
You have to take a call.
how
Right.
many levels we have to make?
Our goal is not to use, how many labels, and this term is known as depth. At what depth we wanna go? Depth 8 means we can go at most 8 decisions in between.
So, just that first example you mentioned, like there are 1,000 cases, so there are 100 defaulters and 900 non-defaulters.
This is the original data.
Original parent. So we calculated the parent entropy for 2 different candidates, and then, but when you go to the child one, just that number. So when let's say you mentioned 60 defaulters and then 800 or something non-defaulters. So the entropy at that node will be 60 by 1,000.
Entropy of this node here.
Yeah. So the probability, like now minus.
Yeah.
2.
Entropy of this node
Yes.
would be 840 upon thousands. Overall, 840 candidates. 840 rows lands up here,
Mhm.
and 160 lands up here. 860. 860 here, 140 here.
860, 140. Okay.
Yeah. So entropy of this guy would be, so here, entropy of child one. So let explore this totally. We got 60D, 800 ND. So entropy of child one, this guy would be 60 upon 860
Yes, exactly.
log
Log
60 upon 860
plus
plus again what is 800
8
upon
upon
860
860.
same log this number,
Correct.
right? Suppose this came out to be 0.25, for example.
Yeah, exactly.
Then same, suppose this came out to be 0.35.
Yeah.
When we sum up, then we will do 860 upon 1000. We are weighting it up, right?
Yes, exactly. Yeah. So
Eventually,
firstly,
eventually, this guy is EC1, entropy of C1, entropy of C2.
we add it.
We have to add it, but we cannot add it directly. I mean, this guy carries more weight, 860 rows. This guy carry 140 rows.
Okay.
So we have to neutralize it or normalize it. How we do that? Simple. 860 out of how many candidates? How many rows? 1000. 860 upon 1000 into entropy of child one plus. So this is weighted entropy,
Okay.
right?
So directly we are not adding it, but we are
No,
just
yeah, right.
normalizing it.
Yeah. So this is one, and this you keep doing it, right? Okay, so any doubt in this? Any doubt?
I go downward, like downward mode.
Yeah.
So, can I use same column again if I'm going down? So once that column is, I
One
will
column is utilized, is utilized.
okay, gone.
Otherwise, it will not make sense.
But it will then can loop it again and
Run थोड़ा सा loop.
तो कितने percentages हो जाएंगे ना?
Because if ऐसे सोचो, if you have taken the condition petal length less than 1.75, so all the guy for whom the petal length was less than 1.75 is already here. If you again apply less than 1.75, all are less than 1.75, right? You cannot loop it. So that condition is totally consumed. Right? Okay. So see, can you see the top one? Here there are two classes. Classes negative, classes 0 on the left hand side, classes 1 on the right hand side. And right now in the bucket, there are 5 red, 5 green. So you will see this is the pure impure class, what we understand so far. So therefore, entropy is highest, 1. It's always between 0 to 1. Right? If I mean this was one of the net is not working, otherwise we could have moved, balls here, you will see the entropy moving accordingly. So if you remove, say if you make one negative class into green class, so you can see that these are the balls. If you remove one ball from red to green, then that class will become pure towards green. 6 greens out of 10.
Yes.
Purity goes towards green. 7 out of 10. Purity goes towards green. Therefore, you see this starts landing up. So as we move towards positive class, entropy starts going towards 0.
So bell curve kind of.
Yeah, normal curve. I mean, see, if we adding more negative classes here, it means that it is moving towards a pure red class. So you will see the curve going towards red. Impurity goes towards 0. All red, no green, impurity 0. Pure red class. All green, no red, pure green class. Impurity always 0. So consider impurity is a noise, right? If 4 of you are computer science, 4 of you are electrical, mixed class. Impure means mixed class. All computer science, pure class of computer science. This is the idea. Our goal is to segregate or use decision boundaries in such a way that eventually we get a separate set of pure class. In practical, it won't be possible. Each class will have some purity, right? There might be the case the bank took the wrong decision, defaulter becomes non-defaulter. So these cases exist. But majority is to reach 80% pure impure class. Okay, right? So with this, you already see information gain is nothing. Entropy of parent minus average of children. Average is same what we discussed, weighted.
Weighted.
You weighted. Okay, now just theoretical part here. The algorithm which we see, this is known as ID3. ID3 focuses on information gain. Right? ID3 algorithm. However, machine learning uses algorithm which is known as CART, C-A-R-T, right? Same concept, only the formula will change a little bit. Higher information groups.
And some of them, and some of the things. Except and also very good. डिहाइड्रेशन की वजह से मसल वीकनेस इलेक्ट्रोलाइट इम्बैलेंस
Okay. So, yes,
No,
okay.
get the AC.
Wait करो. ये this is a site. I mean, you can अभी आप demo देखते हैं. I mean, this is kind of a live demo of how decision trees makes one by one. But अभी चल नहीं रहा है तो you can just write it. And I mean, this is self-sufficient to understand decision trees and for us. So the same way they will teach that the class is impure and you move some, you take a decision boundaries, how the decision boundaries are created, concept of information gain in a virtual live demo method.
So I have just one question before.
Yeah.
So these regression methods or the classification methods, so when we start doing it in Python, so there will be some inbuilt library.
Yeah,
inside.
different library. So eventually we're gonna do that thing. We're gonna see the Indian logistic and decision kind of.
Recently through
Yeah, Jupyter note. One day will be totally practical. So same problem getting solved by decision trees,
decision tree.
whatever logistic. Now, I mean, I think that's right. नहीं चलेगा है. So now, okay, yeah, sure.
Like then in that case, when we do that, we will take our training data.
Yeah. I'll provide your data.
Okay, you'll provide the
Yeah,
data.
yeah, training
then we
data,
will-
test data,
we will, okay, training and test
training
data.
test.
We can-
And you have to split. Then you have
the test data.
you have to create a model, train it,
Training.
fit, and then same calculation. Then you wanna see the same confidence matrix, and then you're gonna see that I'll go with the random forest or logistication based on confidence matrix. Somebody would be having higher or lower precision. Your call. Whom should you go with?
Oh.
Okay. Meanwhile, just tell me this we have classic point. But if suppose I want to use decision trees for continuous data predicting the salaries, then what will happen? I mean, what will change in this scenario?
didn't understand that.
Decision trees, right? You saw the example of splitting into multiple classes, class A, class B, class C. But I want to use decision trees to predict some continuous data, maybe salary, house rent. Then what part will change here? Decisions would be same. I mean, if something is greater than 50,000, but what something will change in the terminal node, but what it would be? Same, keep the example of salaries. Okay, we start make one decision node. Okay, people this salary less than 50,000. Model predicts this boundary. Eventually, we got some terminal nodes, right? Final thing will be changed to predict the salary of that bucket with that decision tree on a average of average. Take the average of last all the candidates, all the rows which lies into in that bucket. That would be the predicted salaries of all the people who will go through this, I mean, this whole decision take out to 100 rows out of 1,000. So 100 ka salary ka average would be the prediction. And that gonna remain for same for all the people who follows this path or that path. Right?
But for this example, then decision tree is not the right approach.
It's not necessary. So
like what
decision tree is not just couple of boundaries or 2-3 boundaries. The boundaries could be used, right? If you are practically think if you are able to segregate your classes in such a way that all the people who are having same skills coming from same colleges, same knowledge maybe, they are bound to have this expected salary, at least out of India. In India, we do not consider India. Out of India, they would be having good salaries or similar salaries. So their nature is same. So predicting average is fine. We go to Europe, people irrespective of the performance getting same salaries. So that's why decision trees are made to use for education also. Term they're gonna change decision tree classifier in practical machine learning. You will see decision tree regressor. Okay, so we studied ID3. ID3 uses information gain. Now we're gonna understand card. This is the algorithm which machine learning libraries use. So we're gonna see, so there is a library known as scikit-learn, open source and very well maintained community. And this is the go-to in production as well for classical machine learning problems, right? So scikit-learn decision tree uses card. Region is just that it's the computation is a little faster and there are multiple regions, but this is complicated. Card entropy formulas were discussed minus P log Pi. Card works on a term which is known as we generally pronounce it Gini. Somebody calls Gini, but mostly it is Gini. Gini index. This is the term which replaces entropy in card. Gini index is nothing. It's 1 minus summation of probability ka square.
Okay, so they have some different method to
Even different method to
segregate.
find the best node.
Yeah.
Right. So Gini index of parent Gini index would be same formula. In parent, we have 100 defaulters, 900 non-defaulters. So defaulter probability would be 1 minus 100 upon 1000 per square plus 900 upon 1000 per square. Right? Lesser the better. But we will use the same concept. We will use the Gini index of child. We will weight it, we will average it. We will subtract it. That will inform, that is called information gain here. Here it is called as Gini gain. Higher the Gini gain, better is the division or better node it is, right? So
what is that card?
card is classification and regression trees. I'm not sure is the full form. Maybe Google करके देखना. But this is something like, or like I said, let me check. It is C.A.R.T. Let me check card full form. Card full form.
The Gini gain should be as much as close to zero.
Zero is the best case. We see in the graph. If entropy is zero, it means pure class. Entropy,
Same. Gini gain also same.
Gini gain also higher the best division into different classes. But best thing to understand the concept is always IT3 information gain, right? एक और चीज है entropy. Entropy, these terms again came out from the whole concept came out during World War. World War, I mean the minimum number of bits required to send the information to the third party. Right? So they wanted minimum number of bits.
So it's to say classification and relation tree.
Okay. So they call it card algorithm used in same decision tree, but for scikit-learn library. Earlier they also used IT3 Maybe you can check IDC full form or some information dictonomy ऐसा नाम है. But that's okay. That's theoretical part.
So the Gini index is one form of uh, like instead of using an entropy directly, we use a Gini index, which will further classify pure and impure.
Yeah. So Gini index of parent minus Gini index of child summation difference Gini gain.
Oh.
This is also a gain. Better the gain, better the splits. Okay, just tell me one thing here.
Sorry?
If this class is purely pure class, then and suppose there are 100 defaulters. After segregation, say 800 non-defaulters, 0 defaulters. Probability of non-defaulters would be 800 out of 800. 1. Probability of this guy would be 0 upon 100. 0. Put it here. 1 का square. Summation कर रहे हैं ना 1 का square plus 0 का square. This is 1. 1 minus 1. 0. So lower the better. Right? Gini index lower the better. Entropy case में again lower the better.
Lower.
0 the better. And since it is probability, it will never go lesser than 0. Never go more than 1.
Probability of non-defaulter and defaulter, we are summing up.
Yeah, all the जितने में divide हुआ है उनका probability square and then summing up. I mean, in some good cases, they eventually came out to the same. If you do some mathematics, the minus p log pi, उससे जो का nature आ रहा है ना, the pattern which they try to capture, they always boils down to the same thing. ठीक है. So now best part of this algorithm, here we are not, there is no mention of parameters theta 1, theta 2. So that means no gradient descent involved. So it's just that we need to find the best decision tree. Now what could happen? You started now suppose you started with some decision trees and you mentioned, okay, go with 8 level of depth. And somebody says go with 15. What could happen if I allow them to keep on going, grow until they want? So what could be a drawback? So there would be drawback that I mentioned. What do you think? What could be the drawback here? They keep on bringing conditions and splitting into multiple decision boundaries. No time, that's okay. Okay. So suppose we have put RAM, etc. So other than timing, computation.
Computationally, like
Actually, the entropy first of all will increase because we are not stopping at one place. The classification will not.
No, I mean, anyway, for that note, entropy gain, he will take the decision based on entropy gain. But right now, when you are going with the 50 depth, you are making many decision boundaries, right?
Yes.
It means for the cases, so this is basically kind of memorizing the trading data. आपने इतनी decision boundaries बना ली, even for the cases, for example, consider this case here. We are creating, this is star, this is circle. There are the stars here. Right? Stars. एक circle बीच में है. Even to classify this guy, you make multiple decision boundaries. This is not a good case. This decision on all circles are here. So best case could be this thing, right? This could be the best boundary. I mean, I'm okay to make one error here, but just you want to cover, you make so many depth that this guy is also considered as a decision part. This is not right. So you memorize this data. Eventually, जब ऐसा test data में आएगा, so these decision boundaries will take these decision trees. The path which takes us to this part will take wrong decision because this is kind of memorizing. You also try to memorize that one wrong data point. So we have to leave such data set. I mean, our decision boundary has to be crisp, clear, right? So therefore, there's a trade-off of depth. This trade-off, you tell me, anyone, based on our past lectures, how we can do this trade-off. That what level of depth we should go. What do you think? We have trained data test data. This is the hint.
Based on the precision and
Based on the evolution on test data. I'll tab 3. I'll take the decision trees. I'll do the numbers. Tab 4, tab 5. Now I see, okay, tab 5, best answer. After tab 6, 7, test data accuracy or call precision going, haywire. Then that's the point I should stop. So depth is one of the criteria, right?
so confusion matrix is everywhere.
Everywhere. For all the classification, computer matrix.
Based on that only decide our strategy.
So yeah, confusion matrix is agnostic of algorithm.
Okay.
Okay. So this part, that part is clear. The back part is clear. Very impure class, less impure, minimum impurities.
So it means we want to separate out something, but that something else is coming in that bucket. That is the
हाँ, pure मतलब कुछ नहीं है उसमें. Right.
whatever we are trying to predict, it's all everything is there.
There.
That will be pure or
Pure class. I mean, all the classes segregated well, pure class. But in practical, again, as I mentioned, there would be kind of impurities. Decision गलत होते हैं, so that's okay. इस point पे cut करना है कि I'm okay with that much impurity. That's what recall precision accuracy will give you.
Here, we will also see some outliers, right?
Mhm.
They will have to know, like in this,
So maybe-
whatever.
Maybe kind of good answer question, or you say there could be an outlier. Just you tell me how this is better for outlier. This algorithm.
Yeah, so because every time when we go down to the depth, we are further classifying, and then our outliers will be, let's say, it will be segregated.
Partially, yes. You see some column on which we are segregating, that guy contains some outlier.
Let's
1 lakh.
outliers would be you would get from this algorithm. Like
Outliers will not impact your algorithm. You can say how that column on which we are taking a decision, finding the entropy, my decision would be taken, for example, if salary greater than 50,000, but there's an outlier sitting over there, salary 2 lakhs. So that guy is there already classified with the salary greater than 50,000. He has no role to take place or affect the thetas. So no thetas involved here, right? So therefore, this algorithm you can run even before. I mean, it's good to remove outliers, definitely for many things, but this you can run even with the outliers. You can run this algorithm with nulls. That's okay. So let's read this slide once and then advantage, as I mentioned, very easy to interpret and visualize. As a business manager, I do not have knowledge of any machine learning algorithm, but human intuition, I can think. You're able to think, okay, salary greater than 50,000, go this way. I mean, as we see the iris petal example. No, easily capture non-linear patterns. Fewer data processing, as I mentioned, no need to normalize the column. In linear regression, we have to normalize the column because there could be the effect of, one column having more biasness toward the output. If some column is in the field of 1 lakh, 2 lakh, 3 lakh, there are another column sitting there. It's a proportion 0.9, 0.8. Even though 0.9 is a higher proportion, maybe simply maybe imply that this guy is bad or something, but that big number 1 lakh will make that effect of this column 0. 1 lakh ka square plus 0.9 ka square, close to 1 lakh ka square, right? So we normalize it. Here we do not need to normalize because we are just making decisions based on that column, right? So it can be used for feature engineering, predicting missing values. So as in linear regression, we see that if some columns are missing, you can take the mean of that, right? Now I'm seeing there are a lot of missing values. I do not want to go with the mean because there are a lot of missing values. So what I can do, I can create a decision tree, which basically gives me, if this is the case, give them, as I mentioned, that give the average of this bucket. And so this averaging will become the imputation, right? So decision trees helps you do the feature engineering, like putting the missing values, right? Lastly, decision tree has no assumptions about distribution because of non-parametric nature. As I mentioned, parameter when thetas are involved, non-parameter when there is no theta. Coming to disadvantage, so even having such a beautiful nature of this algorithm never used alone, right? Tendency to overfit the training data, the thing which I mentioned, having n number of decision boundaries, so that it makes all the, when actual data, test data comes into the picture, it will make wrong decision boundaries. Sensitive to noisy data, it can overfit noisy data. Small variance of data can result in different decision trees. This could be reserved bagging and boosting algorithm. So for example, so there are algorithms which you're gonna see bagging and boosting. This will come. I mean, they use decision trees. Decision trees are prone to overfitting. Now, there are two terms that I should have told you earlier, but there are two terms here: biasness and variance, or underfitting or overfitting. Overfitting is the cases you train your model so deep that it basically memorizes the data, the cases, right? So when new patterns come into the picture, it is not able to recall it, and it will give you some random answer, right? That is memorization or overfitting. That generally happens when you keep on training it so long, so long that it basically start memorizing data, right? Another one is underfitting, right? Underfitting is what? There is a lot of data, right? You do not use the full data. I mean, you do not use it fully. So you are supposed to train it a longer. You just train it for few epochs and you stop the training.
Okay, so under training kind
Under
of.
training. So underfit.
Okay.
Fit is training.
Yeah.
Fit what is denotes training. Underfit. It's not properly trained even. Right?
Your sample is not like presenting your population actually.
Yeah.
Just
So maybe you train for a smaller sample, which is not the right representation of total population. So when any guy came out of that sample, that is fitted wrong. That is underfit. Now, underfit leads to biasness. You are biased toward this sample.
Yes.
So therefore, higher underfitting, more biasness. Overfitting, you memorize it. So higher overfitting, more variance away, right? So that's the trade-off. So in machine learning also, there is always a trade-off, and this is known as bias and variance trade-off. Right? Bias and variance trade-off. If we go toward higher biasness, underfitting, variance will go down. Right? And so initially, when you this is test data, this is the error. This graph we have seen in the linear regression. When we start training and then we evaluate on the test data, initially we will be having higher error. So we are somewhere here. Then our training will start. Our test data error will start decreasing. Right? Again, at this point, we are decreasing. We are learning well. We are decreasing biasness. Right? As you train well, your biasness will decrease. At some point, this is the optimal area. Some point you do not stop your training. You keep it learning, and right. Same sample. In general, what happens? You give them a set of data, right? You train on that, learn the factor, then again you give next 100 rows, right? Then you make the model, okay, after completing 1,000 rows, again take these rows. Suppose you do not stop this loop, every time you start feeding 1,000. So model sees that data multiple of times. So even if you see a page of data, page 100 of times, you will vote that stuff. Same thing, model to start learning, memorizing it. So your error will start going up. So when error will start going up, it at this point you have started overfitting. Your variance is started. Actual meaning of variance is that at this model, this thetas which has been chosen, if I put this test row 1, it will give me some prediction. If I put this test row 2 of similar kind of data again, it will give me some other prediction. This guy predicted 1,000. This guy, same data with slight modification. Slight modification, few columns, gives me 2,000. There's a huge difference. This is variance. This happens when you overfit the data. So that's the variance. This part is biasness. This part is variance. I want a trade-off, which is this part. This is why I said very.
Like expecting that graph should go flat. So if I, if I like giving same kind of data again and again, it will reduce the error initially when the data is new. Then again, it should go flat. Why it's
That is for train data. This is test data.
okay? You are saying that that side it's
Train data में तो you started memorizing, so error will always decrease or plateau, flatten. But
okay,
here,
you are saying this is test data.
yeah, we always evaluate from test data. So that's our true nature.
So who said is TCD we?
Yeah, that concept is yes, but that's before training in linear regression. अगर मेरे डेटा में वेरिएंस है आ रहा है तो इसको मतलब हेट्रो नहीं होना चाहिए राइट तो होमोडोस्कैटिक मतलब टुवर्ड्स सिमिलर वेरिएंस
मल्टीपल मिलते हैं एक ही उसके लिए।
हाँ एक ही के लिए अगर मैं देख रहा हूँ अलग ही प्रेडिक्शन आ रहा है तो वो वेरिएंस प्रेडिक्शन ऑफ वाई प्रेड फॉर सेम डेटा इज यूज्ड दैट heteroscedasticity.
So in this half portion where it's decreasing, so that will be the same data we use for training. Here it will error will be less.
So here this data is train test split. Model trains on train data.
Yeah.
Test data he knows nothing. So therefore he is bound to make error during the overfitting. So this is not a bivariance trade-off. तो वही चीज हमने डिस्कस किया है और डिसीजन इसके साथ क्या था एग्जांपल कि ओके मैंने I started with root node. Somehow I did not plan it well, or somehow in my train data, I started with column 1, column 2. I'll go with optimal depth of 8, for example. But I have not seen actual test data. I mean, you see the data which is provided by you, train test. But after next year, some new data came up, and then I see that this decision tree is failing, right? Because indirectly it makes decision boundaries which were apt for that data at that point of time.
Yes.
But for that new data, still they are too much of decision boundaries, right? So what could be done? What could we have done?
If that present, we can take our decision tree and
It is
relevance.
This is before coming up new data, next year's plan, for example. So what you could have done, what you could have made one decision trees, right? Then, for example, with column 1, now you could have made decision trees with column number 10. A whole decision tree. I mean, fully grown decision trees, level of depth 8. Another decision trees with some other column. As of now, for our cases, maybe column number 5 is not the right point or root node to start. Cart algorithm says okay, go with column number 4. That's okay based on this data. But I say maybe I should go with column number 5. Right. So I do the same decision tree fully grown with column 5. I make 100 decision trees, right? And then what I do, finally, I take the average of decision trees. So this is called, this thing is called as ensembling of decision trees and bagging. And this leads to the another algorithm, which is known as random forest. As name suggests, forest is nothing but the group of trees. Random says, I will choose random root node. So I'll make, this is a decision tree 1. This is decision tree 2, decision tree 3. I make 500 decision trees. We make 500 decision trees. I mean, there's no. Best part is that even if you make 1,000 decision trees, averaging out will balance the stuff. Averaging out has a very beautiful feature that it brings all the things closer to the mean. That's why we call it average. So even you will say that 500 ka bana rahe hain, 1,000 ka bana rahe hain, won't it affect the answer? It won't, right? So, but even it will not improve. So results coming from 500 decision trees, 1,000 trees might be same. So why to go with 1,000 trees? So in Sabka, this guy says for this row, this is class. Yes, I mean class 1. This say class 1, 0, 1. And we will see out of 500 decision trees, 400 says class 1, 100 says class 0. So I will choose. So what it does, maybe one tree would be wrong. This is overfitted. Maybe this tree is overfitted, but we have made 500 trees.
Okay.
So not all will overfit, right? Because this is the nature. I mean, some will overfit for sure, some will not. But we are trying to capture, and each tree will grow differently. Column 1 started with column 2. So column 5 might start with column 45. You know, so so each try to capture different aspect.
That's so basically exploring multiple possibilities.
You are exploring the whole forest, and so now these algorithms are known as terminologies are known as ensemble methods. And the thing which we discussed, random forest, is an ensemble methods, which is a part of bagging algorithms. Bagging algorithms. What bagging algorithms suggest? Now look at the data. These are rows: row 1, row 2, row 1000, column 1, column 2, column 3, column 50. Right? Bagging algorithm says that in fact what random forest does, I mean there are two probabilities. I make different bags of columns. I will not suppose what happened if you use all the columns, all the rows to create the very first decision trees. सब डेटा दे दिया, सारे columns दे दिए, the algorithm will bring the best node. So every time if we provided whole data, it will come up with the same node as the best root node, right? क्योंकि उसको तो पूरा डेटा दे दिया, so he will do the same calculation minus log p1, वो हमेशा same ही आएगा. You are providing them all the rows, all the columns. So what these guys yeah, instead of giving the all the columns, we will give them just say 10 columns, rows. So this guy is bound to take the decision of the best column out of these 10 columns. So suppose हमने अभी हम पे 10 column ही, for example, C1, C2, C3, we have 10 features. To first decision tree, we give them C1, C2, C3, C4, इनमें से decision लो, and give me a fully blown tree. Next time we say C2, C3, C5, C9 में से decision trees लो. This guy is bound to take the call out of these 4 trees. So basically what you are giving them a selected set of columns rather than full column. So each set of column are bound to grow differently from this set. This way you make them forcefully make the independent decision trees independent of the others. Also, you see we are keep C2, C3 here, C2, C3 here.
So creating possibilities.
Three possibilities. Maybe there could be the case that C after C5, C2 could be a best subset. If I do not provide them C2, we might miss the opportunities. So we will give them the overlap set of columns.
How do you decide which columns to choose, or based on that decision?
That decision is known as randomly.
Okay.
But they are formula. They are formula m by 3 and under root of m. M is the number of rows. एक और चीज होता है, instead of giving all the rows, we give them a subset of rows. Right?
Say
We'll take the calls. But एक ही होते, we blown it to 500 decision trees and so on and so forth. Right? So that's, let me show you the decision first.
If we give all the columns at a time, it will make only one tree.
Of course, the formula is just minus p log p. वो change नहीं होने वाला because you have already given them the full set.
But what if like there is no logical relationship between C1, C2, and C3? Because if I force
That would be the case. That decision trees will give you but we are making hundreds of decision trees. तो उसने zero दे दिया, but if we
automatically it will go outside.
yeah, so if you make a jury of 100 people, not all jury will be bad, right?
That statement, I think, that makes sense. Right? It leverages the power of wisdom of the crowd. So
By combining prediction from multiple decision points to improve the accuracy. तो जैसा मैंने बोला ना, bootstrap bagging को एक और चीज बोलते हैं bootstrap aggregating. Bootstrap का मतलब as name suggests, bootstrap is a selecting choosing a selection and then aggregation on top of that. Random forest uses bagging to create multiple subsets of training data by randomly sampling with replacement. With replacement means same data का छोटा सा portion we provided to the other decision trees, right? Each decision tree is trained on a different bootstrap sample. हम sample को भी overlap करते हैं. Why? Just to take the consensus.
Can I do in this way? Like, let's say I have 5 columns. Maybe I will start with 2 columns. Then I will have 1, 2, 3. Then 1, 2, 3, 4.
कर सकते हैं, yeah.
5.
But yeah,
So there will
ideally
all
कर
the
सकते
possibilities.
all the possibilities, but but this thing is taken care of. So वो उन्होंने पूरा ही ना बेस्ट सारा सिलेक्शन लेके एक पैकेज बना दिया है. You have to call it, you have to provide it, how many depths, how many decision trees. So ये decision trees, if they are called decision trees, but when we refer it in terms of random forest बोलता है कि what is the base estimator. Base estimator. So my base estimator is decision tree. Number of base estimators 500. So उसमें आपको random forest में you have to provide the definition of decision trees too. वो पूछता है all that is कितने disease चाहिए 500, thousands up to us. Right? There are many features we're gonna see during the practical. 10.
Every time so it is random, right? So every time we change or change the like numbers or rows or columns, something we change, we'll get some different results.
Yeah.
Ultimately, right? So is it the scenario if we train
So
using one?
there is a term known as seed. Seed. If you fix the seed, they would be recoverable. I mean reproducible. So every time they will choose the same set of rows and same stuff. So ऐसे ही करते हैं. I mean when we are doing an experiment, we keep the seeds same. So that
Because
otherwise they will
should be
yeah.
we won't give the same results every time.
Definitely.
Everyone would get something different.
Different results. So एक बार सब कुछ prepare हो गया, then we will fix the seed and then we always use the same seed.
I'm sorry. We stopped today.
Yeah, it's already time. So इस algorithm में there is not much to go into technical aspect,
Yes.
but we have covered linear, logistic, random forest, decision trees. It's better to all these things.
Yes.
And then we stop the supervised, then we will go towards the unsupervised, in which you would not be having label, you would be having just data, you need to predict the clusters. Cluster 1, cluster 2, bad customer, good customer, arrow customer, right? And after that, there are 2 algorithms in that. After that, we will go into the Gen AI algorithms, maybe.
Okay.
And then we will close all this. So I think 4 to 5 lectures are remaining.
Yes.
1 month we have.
Yes. I think we can extend like
If required.
we can have Sundays also.
Sure. I'll share the slide.
Sure.
Charging the ring and charging नहीं है. तो some people are better. आज वैसे भी नॉट चलेगा. आज नॉर्मल सैटरडे को निकल जाएगा.
हाँ, link दे देना.
सीधा ये एक्चुअली ये ना फॉर्मल है ना, फॉर्मल आज नहीं है.
हाँ,
तो ना मेरे को वो आंसर शीट्स लेना था, तो किनसे ले सकता हूँ? सुनील मैम से.
सेम में भाई है.
आई है ना?
हाँ, आई है.
उनका किधर है केविन?
कैप्टन बताता हूँ इधर.
ठीक है.
Yes. I'll let you. इनसे ले.
ये तो फिर नहीं बच्चे को
हाँ?
next है.
अभी है. चलो इधर ही चलते हैं बाजू में.
मतलब
मैडम मैं स्नेहा मैम आएंगे. ठीक.
चलो वो भी ऑन टाइम तक करने को ऑन टाइम को ब्रेक ले पाएंगे नहीं करता ऑन टाइम अच्छा ये रिकॉर्ड
गुड.